Yeah. We are now live.
Cool that we're not live. Okay, so welcome everyone. We are right now with our awesome next session. It calls Deep Dive into fairness and machine learning with Fairlearn. And we proud to experiment today with a new setup. So actually, instead of just streaming to YouTube, we let everyone in to make sure that for Q&A there is much more space for it. So I will start with a basic set of rules, then switch to who are PyLadies Amsterdam, and then we switch straight to Hilde with her awesome workshop for this evening. So basic set of rules, there will be some Q&A. If you have any questions to Hilde, if it's not really urgent, you can just type it in and we're gonna ask Hilde to answer this question as soon as the appropriate time comes. If you feel that your question is really, 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 really important right now, you can raise a hand here and just unmute yourself and ask this question directly to Hilde. Or otherwise, we have a lot of time, I suppose, at the end of the evening for your questions. So that's basically it. We stream everything to YouTube, so in case you miss something, you can always rewatch it. And without further ado, I will switch into our PyLadies Amsterdam part. So, PyLadies Amsterdam, we are a local Amsterdam chapter of Global PyLadies Amsterdam. We don't do Pies, fortunately or unfortunately, we do Python, and we make sure that everything that we do is actionable. That's why you are part of this workshop today. And it's nice to see all organizers here in one call. So hello to Bhumika, hello to Nancy, and hello to the rest of the team. But now I think it's high time to switch to a beautiful presenter who already did a session with us on introduction to fairness. And now we're gonna literally deep dive further. Hilde, time and space is yours.
Awesome. All right, so hi everyone. My name is Hilde Weerts. I'm an artificial intelligence engineer at Eindhoven University of Technology in Eindhoven, so in the southern part of the Netherlands. I'm just gonna see if I can start sharing my screen. All right. So you cannot see my face anymore right now, but we will try to see if I can turn on the camera when we actually start the tutorial. But for the slides, it wasn't very nice because then you can't see all the slides. All right. So as already introduced, today we're going to do a deep dive into fairness and machine learning using Fairlearn. And the agenda for the presentation part of the workshop. So first I'm going to do a little recap on what algorithmic fairness is and some of the other things you may have already heard in the previous workshop I gave, an introduction to algorithmic fairness. And then I'm going to give a short introduction to the case study that we're going to investigate in this tutorial. So first, an introduction to algorithmic fairness. So if you are attending this workshop, then probably you have already heard of algorithmic fairness before. But basically, the idea of algorithmic fairness is the idea that algorithmic systems should behave or treat people without unjust or prejudicial treatment on the grounds of sensitive characteristics. So with sensitive characteristics could basically be any type of characteristic, but in most cases, this will be things that are, for example, protected by law, like gender, sex, race, ethnicity, stuff like that. But it can depend on the context, which sensitive characteristic is of interest. So here I have a few examples from the news and from other sources. So first of all, we have a hiring example. So already a while ago, I think this was 2016 or something like that, there was this news post that said, oh, Amazon scraps secret AI recruiting tool that showed bias against women. So what happened in this case is that Amazon was training a machine learning model to predict based on somebody's resume whether they should get an interview or not. But it turned out that this algorithm gave somebody or penalized people's resumes based on whether they had the word women on their resume. Like, for example, in a women's chess team. Or maybe if somebody would have PyLadies Amsterdam on their resume, then maybe that would also be picked up by the algorithm. To be clear, this secret AI recruiting tool was never actually deployed. I also doubt it was really secret, but I suppose that doesn't make as good of a clickbaity title. My assumption would be that they were just developing it internally. Another example close to our hearts in the Netherlands, there was something called the Dutch childcare benefits scandal. So what happened here is that there was actually a very, very simple algorithm that was being used to determine whether somebody might be fraudulent in their childcare benefit applications. And this algorithm specifically relied on whether you had a double nationality or not. And this hurt a lot of people who were accused by I don't actually know which specific organization gives out these things, but anyways, so by the organization that's responsible for childcare benefits, they were actually accused of being fraudulent, even though in many cases they weren't, and this caused a lot of harm. And a final example is this one. So this is already an old example. But what happens here is that we are translating from Turkish, which is a genderless language, to English. And you can see that the translations are quite stereotypical in terms of occupation and gender. So in Turkish, you do not really say she or he. You can just say, I don't really know how to translate that to English without the she or he, but you can see that the translation is quite stereotypical, with she is a nurse and he is a doctor. So these are just a bunch of examples of where things can go wrong. But generally speaking, we can distinguish between at least 6 different types of harms, of fairness-related harms. So first of all, there are allocational harms. So these are the types of harms where the system extends or withholds opportunities, resources, or information from some people, so some groups of people, compared to other groups of people. So here you can think about the ability to get a job, to get a loan, stuff like that. A second type of harm is quality of service harm. So this is a type of harm where the system simply does not work equally well for all groups, even though not necessarily something specific is being allocated. So here you can think about, for example, a facial recognition system that only works if you have a white skin. That's an example of a quality of service harm. There's also representation harms. So here we refer to cases where the development or usage of the system overrepresents or underrepresents certain groups. As you might can imagine, this can also be a source of some of the other harms, like quality of service harm. Like if you do not have enough data of a particular subgroup of your population, then maybe your model isn't able to learn things as well for that group. But also more generally speaking, over scrutinizing a particular group of people, for example, in fraud detection, or even just ignoring that they exist, can already be harmful as is. Then a fourth type of harm is stereotyping harm. So here, this is, for example, with the translation example, here you can see that a machine learning model was reinforcing existing stereotypes. So this type of harm is particularly prevalent in unstructured data, so like images and text, because they can be quite deeply embedded in those data sources. Then a fifth type of harm is denigration harm. So this is a type of harm where the system is actually actively derogatory or offensive. So the example that I usually use here is of Google's image recognition system, that at some point when somebody with a darker skin in the United States, they uploaded a photo and then it got tagged as a gorilla, which is obviously quite offensive if you categorize somebody as an animal instead of an actual person. So this is an example of a denigration harm. Another example would be if, for example, some automated chatbot starts splurting out derogatory slurs or something like that. And then finally, there is procedural harms. So here we do not necessarily consider the outcome directly, but we are thinking more about the way in which the system makes decisions. So this is, of course, closely related to interpretable machine learning, because you need to be able to understand how the machine learning model comes to a prediction in order to have a judgment about whether you think that is correct or not. So here we can think of, for example, if the machine learning model uses particular features in a way that violates social norms, like getting penalized for, in a resume selection model for having a lot of experience that typically doesn't really coincide with our values. So that's just an example of procedural harm. So in the fairness literature, most of the literature is focused on allocation harms and quality of service harms. And in this particular tutorial, we're also going to focus on these, but I always like to give this overview because it can be quite helpful to distinguish between all the different types of ways in which fairness might be violated. So a picture I always get back to is this little visualization of the machine learning development process, because many of the fairness related harms can actually be referred back to the decisions that we make throughout the machine learning development process. So that ranges from formulating your problem, collecting the data, actually training your model, then making decisions, and then there's also so first making predictions and then also making decisions. And then, of course, the impact is what's happening in the real world. So typically, fairness-related harms can arise because there is some sort of a mismatch in the way that we develop a system that doesn't, in a way such that it doesn't coincide with our values. So just to give you a few examples, in your problem formulation, you can think whether your problem formulation actually reflects the real world context that you are considering or the moral values that we have. So are we even solving the right problem? Is the way in which we decide our target variable, does that actually coincide with our values? So that's one example. And then the second one is whether the data is a good representation of reality. So is the data that we are collected maybe biased in some way or another? But then there's the question, when we are training our models, are we optimizing so for the right performance metrics? This is like the literal optimization step. And then we have, of course, the question, well, does our system make fair predictions? And the most important part, does the system as a whole actually produce fair outcomes or not? So the notion of fairness that we're going to focus on today is called group fairness. So this is a specific set of fairness considerations that compare the behavior or the performance of a model across sensitive groups. So basically what we do, let's imagine we have 3 groups that we want to investigate, and then a group fairness metric will measure the extent to which some particular group statistic differs across these groups. So for example, we might be interested to see what the maximum difference between groups is. So one very commonly talked about fairness metric is demographic parity. So here what we are interested in is to see whether there are equal selection rates. So basically, is the proportion of positives in group 1 equal to the proportion of positives in group 2? So this is a measure of allocation harm. So you may remember allocational harms, we are looking at whether particular resources are distributed equally across groups. So you can imagine in the resume selection example, is the proportion of female applicants that are invited for the interview the same as the proportion of male applicants or non-binary applicants or whatever gender you are considering? And the main assumption of this fairness metric, because you can see that this fairness metric actually only depends on our predictions. So it doesn't take into account the ground truth variable in our data set. So the assumption of this fairness metric is that the target variable is either not a good representation of reality, or it is a good representation of reality, but reality is biased in some way. So an example here would be, again, in a hiring scenario. So let's imagine that we that we are trying to predict who will be a good employee, and we use historical hiring decisions to measure that. Well, if historical hiring decisions were biased towards certain groups, then our data will actually not be a good representation of what we're interested in, because we are interested in employee quality, not in previous hiring decisions. So in that case, that would be an example where the data is not a good representation of reality. Then if we consider what we want reality to look like, it might actually be the case that some groups are generally better employees, like maybe they are generally better at doing data science, but that is because they, for example, due to gender roles in society, they haven't been able to pursue that type of jobs and education, etc. And then we might say, well, we actually want to change what reality looks like, and that's why we are interested in these equal selection rates. So these are just two reasons why you might want to optimize for demographic parity. So a second fairness metric, the one that we're going to focus on today, is equalized odds. So this is a measure of quality of service harm or allocation harm, depending on what is distributed. And here we are interested in equal false positive rates and equal false negative rates across groups. So I think it's quite easy to see why this would be a measure of quality of service harm, because we are literally considering whether one group, some type of mistake is made more often compared to another group. So here you can see that the formula does take into account the ground truth variable. So implicitly, this fairness metric assumes that the target variable is actually a good representation of reality, or what we want reality to look like, but it might be the case that the data distribution differs across groups, causing differences in predictive performance. And you can imagine that if the number of instances per group differs a lot, that this is only further increased this problem. So that's it for the fairness metrics. So in order to optimize for predictive performance, but with a fairness constraint, so either demographic parity or equalized odds, researchers have been quite productive in coming up with different types of fairness-aware machine learning techniques. So these techniques formalize fairness as an optimization problem. So basically what we do is we try to optimize for whatever we are interested in, like accuracy or something like that, under a fairness constraint. And we can distinguish three main approaches. So first of all, there are pre-processing approaches. So these are approaches that change the data in some way, typically such that the sensitive feature cannot be deduced from the data anymore. So for example, basically we change the base rates, for example, in the data set. But we also try to preserve all the other information as best as we can. Then a second set of approaches, which I usually call constraint learning approaches. In the literature, they also sometimes call it in-processing, but I don't really like that term, but that's just my personal preference. And here the idea is that we can incorporate explicit fairness constraints in the learning algorithm itself. So during training of the machine learning model, we're going to push the model towards adhering to these fairness constraints. And then a final set of techniques are post-processing techniques. So here we assume that you have already trained a machine learning model, but we want to adjust the machine learning model or the predictions of the model to make sure that it adheres to some type of fairness constraint. So for example, either demographic parity or equalized odds. And today we're going to look at two of those fairness-aware machine learning algorithms implemented in Fairlearn and how you can apply these in practice. Yeah, so just to conclude, Machine learning systems can reproduce, amplify, and introduce unfairness. We've seen this through some of the examples. We will focus mostly on allocational harms and quality of service harms today. And fair machine learning algorithms can be used to optimize for these two fairness metrics, demographic parity and equalized odds. So now I'm going to continue to the tutorial part. So we're going to focus on one of the main examples in algorithmic fairness research, which actually sparked a renewed interest in the field. So just for some context, I think the first algorithms that were trying to deal with some form of unfairness mitigation arrived around 2010, 2012, something like that. And then for a while, people weren't really working on these problems anymore. But then after this particular incident happened in 2016, a lot of renewed interest was in the field. And actually now there's like quite a lot of people working on these types of problems. Oh, I see I didn't update this slide from the previous one, but so the goal is not to measure notions of fairness, but to use fairness-aware mitigation algorithms. So the case study that we're going to look at is the COMPASS recidivism prediction case. So a little bit of context. COMPASS was a pre-trial risk assessment tool that is actually, I think it is still used in the United States. And pre-trial risk assessment, because I'm assuming most of the people here may not be familiar exactly with this process, but in the United States, it looks something like this. So first you are arrested for something, and then you have to await your trial. And before awaiting your trial, you can either do this at home, so released, or detained. So if you are detained, you go to jail. And if you are released, you can go home, and depending on whether there is some bail that is being set. So this is what you always see in the movies, that you have to pay some amount of money to be released. So the judge also needs to decide, first of all, whether you will be detained or released, and then second of all, whether there will be a bail set or no bail set. So then you have to await your trial, and then the actual trial happens. So, and at the trial, it is decided whether you were guilty or not, and how you will, and if you are considered guilty, what the consequences of that are. So it's very important to realize that if you are detained, so if you have to await your trial in jail, that this can severely impact your prospects of your process, because when you are in jail, it's much more difficult to prepare for your trial. So you only have limited access to phone calls, limited access to the library and stuff like that. So it's a very important decision for so the judge needs to make this decision, but for the defendant, it's a very important decision. Because it can really affect what their chances are when they actually go to trial. And it's also good to realize that this process of awaiting trial can be weeks, months, sometimes even years. And that sometimes people even just plead guilty because they have already been in jail for so long that it's easier to just plead guilty and then be released with some fine or some other thing, or because they have already awaited trial for so long that they don't have to actually go to prison, that they just plead guilty even for crimes that they didn't commit. So the stakes are high. That's what I tried to explain here. And now it turned out that a tool that is being used by judges in the United States to decide whether somebody will be detained or released, and with or without bail, that it actually failed differently for African Americans compared to white Americans. So what happened, the proportion of false positives for the white Americans was much lower compared to that of African Americans, and the other way around for the false negatives. So a false positive in this case means that you that you might be that it might be decided that you have to await trial in jail, even though you will actually not commit a crime again. So for the defendant, this is the worst outcome, right? A false positive. And a false negative could mean that some dangerous criminal might be released into society, or maybe that they do not show up for their trial. And And here we can see that this is more often happening for the white Americans. But you can imagine that this is quite that this incident sparked quite a lot of interest in the research community. So in this tutorial, what we will try to do is we will try to learn a new machine learning model without this big disparity in false positive rates and false negative rates. And as you may have already guessed, because I already mentioned it also, but equalized odds, as you may recall, optimizes for false positive rate and false negative rate. So that's the metric that we will mainly consider here. So now I'm going to switch to the Jupyter Notebook. I hope for everyone has been able to access this one. I'm just gonna leave some time to see if there are any questions. I don't see any questions in the chat, so I'm assuming there are no questions so far. All right.
I think only one thing, it will be really, really nice if you make it a little bit bigger. So it will be...
the text, you mean?
Yeah, the text is a little bit bigger, yeah.
Let's see if I can do that. I don't actually know how do you do that in Safari. Is it maybe Command Plus or something like that? Haha.
I think it should be Command Plus.
Yeah, awesome.
Such a computer scientist.
And also, I just want to add one comment for those who join us a little bit later. So if you have questions, feel free to drop it in the chat. So if something urgent, we can ask it immediately. If it's less urgent, we can ask it later at the end of this workshop. Thanks a lot.
Awesome. All right. Then here we go. So I want to start the actual tutorial with a warning. That even we're mainly going to focus on this pre-trial risk assessment tool because it was such a turning point in algorithmic fairness research. But I am by no means saying that we should be using these tools in the first place, and also not that fairness-aware classifications, these algorithms that we're going to look at, are the answer necessarily to these types of problems. And in particular, you have to imagine that these technical approaches, they are usually at a stage that the data is already being collected. And it can be much more useful to already start thinking about fairness way ahead of that. So when you are determining whether you should be using machine learning at all, how you formulate your problem, which data you use, those are all key parts of trying to optimize for fairness. But yeah, I just wanted to make that disclaimer, and also the accuracy of the models that we are training here is actually not that good. So I would definitely not recommend to use these in practice. So this part we can actually skip because I already explained it in my presentation. So first we're going to import just all the libraries that we're going to need. So we have the basic suspects like pandas and numpy. We're going to use some plotting. We're going to use some scikit-learn, things from scikit-learn, and also from Fairlearn, of course. So the first step is to load the data set. So we're just going to use the same data set that ProPublica has collected. And we're also going to pre-process it similar to ProPublica. So I'm not going to explain that into detail, but we're also going to split the data set into a training and a test set. I see that I put this here with the validation set, but actually it's just train test set. Because we are going to try to train a new model. So let's just run this cell. So this is what the data set looks like. So the X-train part. So we have a bunch of features, age, priors count. This is the number of prior offenses. Juvenile felony count. So this is the number of juvenile felony offenses, misdemeanors, and other juvenile offenses. Then we also have a sex male attribute, which is 1 if the sex that was recorded in the data set was male, and 0 if it was female. So that's the only 2 that were in the data set. And then we also have race Caucasian, which is 1 if the race of the defendant is Caucasian, and 0 if it is African American. So we have filtered out all the other races in the data set just to replicate ProPublica's analysis a bit more. And also because the number of instances were actually quite low for these different races. So just a heads up, we do not actually know for sure how exactly sex and race are determined in this data set. So this is the data that was collected at the police department in Broward County, I think. And it's not clear, for example, whether the police officer supplied the race or whether somebody was able to fill it out in the form, because there's also, we do not see any people with multiple races, and the same goes for sex. So that's just something that I wanted to note. So this data set that we have, and then the Y variable here is whether the defendant was rearrested within 2 years. And we can see that the proportion of the positives, just the average of the Y train, is about 50%. So about 50% of the people in the data set was rearrested within 2 years' time. And just for easy presentation, because it's at least somewhat balanced, we're going to use accuracy as an overall performance metric. I'm not saying this is necessarily the best metric in this case, but it's a simple one to understand, and I think it's fine for the current scenario. So just a little recap from the presentation before. Equalized odds. This is, as I mentioned before, a fairness metric that requires us to set the false positive rate and the false negative rate equal across groups. And as I already explained in the introduction, a false positive prediction in pretrial risk assessment can have very large consequences for the involved defendant, as they may have to await trial in jail instead of going home or being able to set a bail or not. And on the other extreme with false negatives, we can see that a dangerous individual might be released back into society. So this is the fairness metric that we're going to try to look at. So I also have prepared, oh, actually, I promised you that you could see my face now. So let me just, can you see my face now or not?
Yep.
Awesome. All right. If anything is not adequately visible, just let me know, and then I can turn it off again. But I think it might be nice to see my face, even though I cannot see my face. So I hope that it's okay.
So what was covered? So if you look at the line, it says metrics. When you state metrics, accuracy, FPR, and FNR. So what is visible? It's FNR false dash, and then after that it's covered with your face. Exactly.
Here?
Yes.
Okay.
Even a little bit after air, there is nothing visible. But before air, it's visible.
Before air?
Before F and air,
yeah,
column false,
yeah.
that air. Yeah, so little
Right.
it's not air, it's N, negative.
Yeah, okay, so then I know I will just stay focused on this part of the screen.
Yeah.
Awesome. All right. So I've prepared a little, some helper function that will allow us to easily evaluate the classifiers. So if you've attended the previous workshop, then you are familiar with metric frames. So this is one of Fairlearn's capabilities to easily measure fairness between different groups. So all this function does is just compute some metrics and including equalized odds and the accuracy on the test set. But we will see in a bit what this looks like. But this is just the score function that we define, so I don't have to repeat that code all the time. All right. So the first thing we are going to do is to train a very simple logistic regression model, just using the regular scikit-learn API. So here we just have the logistic regression classifier, and we're going to fit it, of course, on the X train, Y train. All right, so we fitted the model, and then we can score and see what it looks like. So the things that we are looking at are the accuracy of the classifier, the false positive rate, and the false negative rate, and then split out across the different races. So just to reiterate, so we have race Caucasian, which is 1 for Caucasians and 0 for African Americans in the data set. So we can see that the accuracy on the test set data is 0.68. which is quite equal between the two different races. But we can see that the false positive rate and the false negative rate are very differently how do you say that? Divided across the groups. So we can see that for African Americans, the false positive rate is about 0.3, whereas for Caucasians it's only 0.1, and the other way around for the false negative rate, we can see it's much lower for African Americans and much higher for Caucasians. So here we can see that we actually replicated some of the results of using Compass. Yeah, so it's a similar result. So if we just do nothing, then basically this is the result that we get. So equalized odds computed by the equalized odds difference function in Fairlearn. What this one does is that it basically just computes the maximum difference in false positive rate and false negative rate. So in this case, the main difference here in false negative rate is 0.32. So that's the value that you see here. So that's just to explain a bit what this scoring function does. So as I already explained, the accuracy is quite similar, but the false positives and false negatives are very differently distributed. And now here I just want to quickly highlight again, and actually it's mostly like a critique of using equalized odds in this scenario, is that what I already mentioned in our introduction is that equalized odds implicitly assumes that the target variable is a good representation of what we're interested in, because error rates are only meaningful if the actual ground truth variable is indeed a good measurement of what we're trying to predict. And in the social sciences, people refer to this as construct validity. So this is the extent to which some type of measurement, so a variable in data set, for example, actually measures the phenomenon that we're trying to measure. And this can be a source of downstream model unfairness. So a few of these examples are of possible problems with construct validity is that healthcare costs can be a biased measurement of healthcare needs, because they may not only reflect people's actual healthcare status, but also their economic circumstances, because they have more access to care that is more costly if you have more money. Historical hiring decisions, I already mentioned this example in the presentation. They're not necessarily equivalent to historical employee quality. And similarly for fraud, observed fraud is only a subsample of all the fraud that happens. So if the fraud cases are not selected randomly, so the ones that we are trying to inspect, then there might be some selection bias. So in the context of pretrial risk assessment, what we are trying to predict is recidivism. So whether somebody will again commit a crime after they have already committed a crime. But what we are measuring is rearrests. So rearrest is, of course, only a subset of actual recidivism, because not everybody who commits a crime gets arrested. It's very important to realize that there have been several studies that show that in the United States there is some likely some racial profiling, so biased policing practices. And it's very likely that rearrests is a biased measurement of actual recidivism. So this is just important to keep in mind. So even though we are looking at equalized odds in this case, it may not be like the actual problem may even be worse than this. So that's just something that I wanted to highlight. So this is just what we also already discussed in the presentation. I try to put everything also in the Jupyter notebook so that people do not actually have to go to the presentation if they just want to run the notebook themselves. But just to reiterate, so we have pre-processing algorithms, constrained learning approaches, and post-processing algorithms that can all be used to optimize for predictive performance with a fairness constraint. So the first thing that we are going to do is actually not use any of the algorithms that are in Fairlearn, but we're going to try to manually post-process the decision threshold. So the decision threshold of a machine learning model, what I mean by this is basically if you have a machine learning model, usually it outputs a confidence score or probability. And then based on the decision threshold, you decide, okay, we're going to predict a positive. So for example, a logistic regression model, it outputs a value between 0 and 1. And in the previous step, when we trained our model, we simply used the default decision threshold in scikit-learn, which is 0.5, and we used it for both African Americans and Caucasians. But the decision threshold can actually be a very nice tool in general to decide the trade-off between false positives and false negatives. So you may have seen ROC curves before that plot the false positive rate against the true positive rate. And here you can easily see that if you change the decision threshold, you can get to a different false positive rate and false negative rate. So now we're going to try to see if by choosing a different decision threshold for African Americans and Caucasians, that maybe we can decrease this difference in false positive rates and false negative rates. Of course, this does mean that we are holding these groups to a different standard, because at a different decision threshold, we are deciding it's a positive versus a negative. So that is a direct consequence of using this very simplistic technique. So as we have seen in this table, the false positive rate in the training data was about 0.13 for the Caucasians. So we're going to try and see if we can select a different decision threshold such that the false positive rate for the African Americans is closer to that. So I have prepared this code already. So first we're going to make predictions. So instead of the regular predict, we're going to use predict proba, which will give us the confidence scores of the logistic regression classifier that we have already trained. I'm just converting this to a pandas series because it makes my indexing a bit easier later on, because I'm relying a bit on pandas there. But that's just like, if you would have coded everything else differently, probably you could have just done it in a NumPy array that is returned by the logistic regression classifier. So here I just get the index of the Caucasians in the data set, and oh yeah, exactly when it is 0, so sorry, that's the African Americans. So that's this variable, so IDXAA train. And then we're just going to compute the ROC curve, which plots the false positive rate against the true positive rate, only for the African Americans. So the ROC curve is just a function from scikit-learn. And then we are determining a new threshold based on the training data, at which, at least in the training data, the false positive rate was roughly 0.13. So if we run this cell, then we will see that the new decision threshold for African Americans would be 0.62 instead of 0.5. So just to make it clear what we have done here exactly, I made a little plot. I'm not going to show you all this code, but let me just hide it. I hope this is visible for you, even with my face on the...
Yeah, it's pretty visible. Yeah,
okay.
There's a lot of space in between. Yeah.
Awesome. All right. So what this plot shows is ROC curve, but a group-specific ROC curves. So the orange ROC curve here is the ROC curve for Caucasians in our data set, and for the African Americans, it's a blue one. So if we would have chosen the decision threshold of 0.5 for the African Americans, we would end up here. So this is indeed like the almost 0.6 versus 0.3 that we already saw in the table. And for the Caucasians, a decision threshold of 0.5, we would end up here. So what we can do, what we have done now, is we have increased the decision threshold for African Americans. So with this new threshold, we end up here on the ROC curve, and you can see that it's much closer to the Caucasians in the data set. So if we make predictions with a decision threshold of 0.5 for the Caucasians in the data set, and a decision threshold with the new threshold, which was about 0.62 for the African Americans in the data set, and we run this cell, then indeed you can see that we have severely decreased the maximum difference in false positive rate and false negative rate, because the equalized odds on the test set is only 0.05. And here you can see this quite nicely. So now in the test data set, the false positive rate for African Americans is 0.11, and for Caucasian 0.10. And then the false negative rate is 0.61 versus 0.67. So you can see that indeed we have made it much more equal. The accuracy has dropped a little due to this intervention. But if you recall, the accuracy used to be 0.68. So actually it's not too big of a drop. So whether it is an okay enough drop or not, that's very difficult to say just like this, because I do not have like super deep knowledge about the exact context. But generally, I think we can see that, like, given the amount of this inequality in terms of false positives and false negatives that we have decreased, this drop in accuracy is actually quite manageable. Now, doing this manually, like right now, we accidentally, so we only focused on making the false positive rate as equal as possible. And because the group dependent ROC curves are so close, this actually turns our false negative rate quite equal as well. But you can imagine that if these ROC curves are even further apart, that optimizing for just one of these at the same time may not be sufficient. But there are some algorithms to automatically determine better or not, I mean, more fair decision thresholds. And one of these algorithms is implemented in Fairlearn's threshold optimizer. So this is an algorithm, it's one of the first fairness-aware machine learning algorithms that was introduced in 2016 by Moritz Hart and colleagues. And the idea of this algorithm is, so in the previous step, we already created group-specific thresholds. And this allowed us to choose a different place on this ROC curve for each group, allowing us to control the false positive rate and false negative rates for these groups. Now, this still means that we can only optimize for the false positive rates and false negative rates that are actually on the ROC curve, right? Because you cannot just, you can only achieve for the Caucasian group, for example, you can only achieve everything that's on this line. You cannot achieve things on this line. So, and the same goes for the African Americans. So that's still quite a limited number of possible solutions. So what the authors of this paper came up with is to, rather than just pick two group-specific thresholds, we can also randomize these thresholds. So what does this look like? If we have a score R, so this is our risk score or confidence score of the model, then for each group, we're going to pick two decision thresholds, and we're going to alternate between them. So if the with the probability of PA, so every instance with a risk score that's lower than the lowest decision threshold will become a negative, because no matter which threshold you pick, will always become a negative. Everything higher than the highest threshold will become a positive, because no matter which one of these is selected, you will get a positive. And every instance for which the confidence score is in between these two thresholds, we will randomly pick one of them. And depending on which probability you choose here, you end up on a different spot on the ROC curve. So visually, this looks like this. So we have the true positive rate and the false positive rate, as we always have in an ROC curve. And then now imagine that these are two group-specific curves. So the dashed line is of one group and the solid line of another group. Now what we can do for the group in the solid line, if we choose this threshold and this threshold, and we randomly pick between them, what will happen is that depending on which probability you pick, with which you alternate between them, we can actually end up on this line, somewhere on this line, in the ROC space. So in this way, we can actually exactly end up with these false positive rates and false negative rates. So what we have done by randomizing the decision threshold, we have increased the solution space by a lot, because before we could only pick any false positive rate that's on this line, but now we can also pick anything that's below the ROC curve of the other group. Importantly, this has a few implications. So technically what this algorithm does is that it decreases the performance of the group for which the performance was higher by randomly selecting between these two thresholds such that it's equal to the worst off group, because we cannot improve the performance, like the overall performance of the machine learning model for one group by randomly selecting between the thresholds. We are still limited to everything that's below the decision, below the ROC curve. So basically what this means, we just decrease the performance for the groups that had better performance until it's equal to the worst off group. And the second implication of using this simple post-processing step is that due to randomization, two individuals in the dataset with the exact same characteristics may receive a different classification just by the flip of a coin. And which thresholds we pick and which specific probability that we pick, we can just use an optimization algorithm to carefully pick the ones that will get the highest overall accuracy, for example, while still adhering to the equalized odds constraint. So that's a lot of information. So let's see what this looks like in Fairlearn. So as I explained already, we have the threshold optimizer class. So this one has a few parameters. So first of all, there's the estimator. So this is the classifier that we're going to post-process. There's constraints. So here we can pick a fairness constraint. So in our case, we're going to go for equalized odds because that's the one that we are interested in. There's the objective. So that's the thing that we are optimizing for while adhering to the fairness constraint. So here we can have a few possible inputs. Because we are optimizing for accuracy, we're going to use accuracy score. And then the grid size, that's just some part of the optimization problem. That's not super relevant here. And here also some more practical additional parameters like prefit, which just avoids refitting the given estimator if it's true. And also predict method. So this one defines which method of the estimator is used to get output values. So you may be familiar with the scikit-learn API, where you can have, for example, either predict or predict proba or decision function, depending on which machine learning algorithm you were using. So this is just a parameter that can help you decide, not help you decide, that helps you to define which method will be used to get the output values that we're going to post-process. So in Fairlearn, we try to adhere as much as possible to scikit-learn API because I think many people, many data scientists are familiar with that. So it makes it easier to use. So we just have a fit and a predict method. And in this case, the special thing is, of course, that we have a sensitive features parameter, which we usually would not have. And this is similar to it's just the sensitive feature in our data set. It can also be multiple sensitive features, but in this case, we're only interested in the race feature. And then this algorithm, because we need to know which thresholds we are going to use, it also requires the sensitive feature when we are making the predictions, and it's randomized, and the random state parameter helps you to decide, or not decide, but it helps you to get reproducible results, as usual with the random state parameter in scikit-learn. Just gonna get some water. All right. So now we're going to train this threshold optimizer. So the estimator, we have already trained our logistic regression classifier, which was called LR. So I'm just going to type that in. Then for the constraints, as I already explained, we are trying to optimize for equalized odds. And let's hope I type everything correctly. Predict method, that's predict proba in our case, because that's the one that will give us the confidence scores rather than the 0.5 threshold predictions with predict. And then the objective will be accuracy score. And then in the fit method, I already pre-filled the X train and Y train, but we still need to add the sensitive feature, which in this case will be race Caucasian. And then, wow, I did it good in one go. Awesome. All right, now let's see how this performs. So we can see that, again, equalized odds is decreased by a lot, and the accuracy is actually similar to our manual decision thresholds. But you can see that the values are quite different. So this, in the previous solution, so with our manual decision threshold, we ended up around, let me just scroll up, 0.1011 for the false positive rate and 0.67 for the false negative rate. And the threshold optimizer came up with a little higher false positive rate and slightly lower false negative rate. So I think it always helps to visualize this to get a really good idea of what's going on. And luckily, we have a nice little threshold optimizer plotter in Fairlearn that will make this particularly easy. So here we can see again the ROC curves. So sensitive feature 0, which was the blue one in the previous picture, is African Americans. Sensitive feature 1 is Caucasians, so that's the red one. The yellow area shows us where the overlap of the two ROC curves is. So in this case, overlap, I mean, it basically just means what is the solution space that we can get. So the most outward Pareto optimal solution space, so to speak. And of course, we can only get on the lowest ROC curve, so that's this one. And then the solution that was found by the algorithm ends up here. Whereas the other one with our manual threshold, we ended up somewhere around here. So the actual thresholds that were being found by the algorithm for 0, which is the African Americans, we can see two thresholds, one of 0.59 and the other one 0.54. And with a probability of 0.7, we choose this one. And with a probability of 0.3, we choose this one. And for the Caucasians, we can see that we have an almost deterministic decision threshold because it's 0.99. And with that probability, it's 0.46. And with a probability, very low probability, it's 0.44, which is even also like quite close. So this is quite similar. So similar to our manual decision thresholds, which was 0.5 here, we have increased the decision threshold for African Americans in order to get to this similar number of false positives and false negatives. So these are two ways in which we could post-process our algorithm. But there's also a whole bunch of methods that can be used to learn a machine learning model directly while constraining it for fairness. So one of these approaches is the approach introduced in this paper. And this is actually the algorithm that started Fairlearn. It's called, it's part of our reductions package, and it's called exponentiated gradient. I hope I pronounced that correctly. So what this algorithm does, it's a little bit more tricky to really understand what's going on compared to the post-processing algorithm I showed earlier. But basically, we can think about a reductions approach in general as some sort of a wrapper around a machine learning algorithm. So an algorithm in this case could be maybe a random forest algorithm or a logistic regression, something like that. So in scikit-learn lingo, that would be an estimator. And the intuition behind this approach is what we are trying to do is we will reweigh the data set in multiple different ways. So reweighing in this case means that we will give a different sample weights to different samples. And each of these different types of reweighing the data represents a different trade-off between fairness and predictive performance. And then what the algorithm does is it trains a whole bunch of classifiers, all of the machine learning algorithm that you put into the wrapper. And then it creates an ensemble out of that. And then based on some probability scheme.
I suppose the compute was ended.
Live streaming is on.
Okay, and let's give approximately less than 1 minute to make sure that it's running on YouTube, okay?
Yes. Just let me know when I can get started again.
Sure.
Oh, thank you, Claire. That's a really nice comment in the chat. And welcome to Amsterdam. I don't live in Amsterdam, but still welcome.
Bhumika, you can give us a go, or?
Just a second. Yeah, it seems to be live streaming on YouTube now, so go ahead.
All right.
Thanks.
Awesome. Then we're going to continue. So as I was explaining, the exponentiated gradient, let's see, where was I? Yeah, so basically what this does is it learns an ensemble of classifiers where each classifier represents a different trade-off between accuracy and fairness. And then by randomly choosing between these according to some predefined randomization scheme, we can actually optimize for fairness using any classifier, any underlying classifier or classification algorithm, I should say. As long as it accepts, of course, class weight or sample weights as a parameter. So, and just to explain the name a bit. So first of all, reductions refers to this wrapper approach, which is called a reduction. And the exponentiated gradient, in this case, refers to a specific optimization approach that is used to optimize for fairness using this approach. We also have something called, is it just called grid search? I think it's just called grid search. That's a different approach that you can also use. But the exponentiated gradient uses the exponentiated gradient descent to optimize, to solve this optimization problem. So a few things that we can already note based on my explanation. So first of all, the exponentiated gradient actually does not require access to sensitive features at training time, which the threshold optimizer, of course, did, because we need to know to which group an instance belongs in order to assign a particular threshold to it. And similarly, there is some aspect of randomization. Again, this can mean that two individuals with the exact same characteristics can receive, I think this should be a different, they can receive a different, I'm not going to change that now, but they can receive a different prediction. And something that's particular about this algorithm is that we are learning an ensemble of classifiers. So by doing this, we by default, of course, sacrifice some interpretability of the underlying estimator. Because if we would use just a vanilla logistic regression model, we can fairly easily just inspect the coefficients to get an idea what is going on. But if we are training on an ensemble of logistic regression classifiers, this already becomes a lot more difficult. So you will see, if you learn more about different types of fairness-aware machine learning algorithms, that in many cases, some form of randomization is used because it can be very helpful in optimization, but it doesn't necessarily mean that it's the right approach to do this from an ethical point of view. But we will get back to that at the end of this tutorial. So regarding the implementation of exponentiated gradient in Fairlearn, it has a few parameters. So similar to the threshold optimizer, we have an estimator parameter. In this case, it's not a pre-fitted one. You can also just pass a non-pre-fitted one. And it should have a fit method, including a sample weight, as I explained, and also a predict method. Then we have a set of constraints, which we need to define specifically using a moment object in Fairlearn. So we cannot use a string here, but that's quite all right, as we will see. So the epsilon decides the maximum allowed fairness violation of the violation of the fairness constraint. And these are just a bunch of things that are related to the optimization. So we have a number of iterations, a convergence threshold, the learning rate. In most cases, we will not change these a lot. And then there's, of course, sample weight name. So this is similar to the predict argument of the threshold optimizer. So here we define what the name of the argument is in estimator fit, which applies the sample weight. So in scikit-learn, this will usually be the sample weight parameter, but if you are using something else, then you can use a different one here. And then, of course, there's the familiar methods. So we have a fit method, again, including a sensitive features attribute, and then a predict method, excluding a sensitive feature attribute, because as I already explained, we do not need it at prediction time for this algorithm. But we do have a random state one again, in case you want to get deterministic results, which is particularly useful for reproducibility. But all the nice optimization bounds and everything do not hold if you make it a deterministic classifier, of course. That's more of a technical detail. So now we're going to train this classifier. And we're going to use, similar as before, a logistic regression model as a baseline. So logistic regression. Then for the constraints, so we're going to have to use one of the moments implementations. And because we are optimizing for equalized odds, that's the equalized odds moment. So that's a class in Fairlearn. So it looks like this. So it's actually similar to the logistic regression, but then an equalized odds, just a class. And then for the epsilon, we're going to pick 0.01 because it's usually the one that they pick. And then we're going to fit it with an X train, Y train, and then we still need to supply a sensitive feature. All right, so this one takes a little bit longer because you have the whole optimization process, but still, because it's a fairly small data set, it's quite reasonable, so it's already done. And now we're going to score the learned ensemble. And then we can see that, again, the equalized odds difference is 0.03, like before. On this particular data set, and using this algorithm, the accuracy is a tiny bit lower than what we have seen with the other two approaches. That's not necessarily a generic results, and these are fairly close to each other regardless. We do see that we end up in quite a different spot in the ROC curves, because we can see that the false positive rate on the test set is now around 0.33, whereas if you may recall, it used to be 0.1 or 0.11 for the manual post-processing and 0.16 for the threshold optimizer. So you can see that this is quite a different solution. For the false negative rate, similarly, of course, the solution is a little bit different. Yeah, so that's all I wanted to explain regarding these, the implementation of these specific algorithms. And now I would like to invite you, and I think it would be really cool if people can also talk a bit in the Jitsi, but if you do not feel comfortable, that's of course perfectly fine. But just to recap a bit, we've showed several ways to use some sort of a fairness-aware machine learning approach to either post-process an existing classifier or to learn a classifier from scratch that adheres to a fairness constraint. So we looked at the manual identification of group-specific decision thresholds. We've also considered this automatically identifying randomized decision thresholds with threshold optimizer. And finally, we also looked at this exponentiated gradient approach that takes into account the fairness constraint directly when learning an ensemble of classifiers. But this is these are all just very technical approaches trying to solve a very complicated problem. And the first thing that's always nice to consider, these are just some questions that you can ask yourself. I'm not gonna look into this in too much detail now. But one thing I am personally quite interested in is to consider in which cases using these algorithms actually makes sense from an ethical perspective as well. So as I have already explained before, most of these algorithms, they use some form of randomization. And you can imagine that maybe not in all cases you would like to have randomization, because the idea is that we are trying to increase fairness somehow. So is it actually fair to randomize a prediction? Like, does that make things actually fair? Like, even though it makes it easier to solve fairness if we view it only as an optimization problem. But of course, this is something that will have actual influence on actual people. So if you go back to this pre-trial risk assessment scenario, if we use randomization, what we are doing is determining whether somebody will await their trial at home or in jail. I mean, of course, it's not just like there's the judge who decides things and etc. But still, it's a heavy decision with very heavy consequences. And would we want that to depend on the flip of a coin? I am not super convinced that in all cases we would like that. Again, there's also this relationship between fairness and interpretability. So for example, the exponentiated gradient approach trains an ensemble of classifiers, and this decreases the interpretability of the approach, even though you can also imagine that for many people, being able to understand how a model comes to its decisions and whether you think that's a reasonable way to come to that decision can also be a particular interpretation of fairness. So this is not necessarily to say that these approaches should never be used or that they are rubbish, not at all. Although I would say that maybe the threshold optimizer shouldn't necessarily be used in most cases. But I just want to not give you just the technical implementation details and then be like, okay, you go ahead and solve fairness. No, I think it's really important that if you are really trying to solve a fairness-related problem, that you think very carefully about all these decisions that you are making, including whether the particular fairness-aware machine learning approach that you are using actually makes sense also from an ethical perspective and from a practical perspective. So try to view fairness a bit less as this technical optimization problem and try to think a lot about the real world consequences of doing these types of things, because they have real world consequences, and that's the thing that we are actually interested in to solve. So that's just my little rant about how fairness-aware machine learning algorithms may not always be the best thing to do, because you can also already start earlier in the process, right? In this case, for example, we are using rearrest data because that's what's available. But maybe we can also collect some different data that's better suitable for this problem. You can also wonder whether we should be using machine learning at all for pretrial risk assessment. So that's also something to think about. So in all these steps, before you even get to the machine learning part, there's already so many things that you can do to improve the fairness of your model. So try to keep that in mind the next time if you are actually training a model to be put in production, and try to make sure that it's not just an afterthought and something you're going to fix at the machine learning stage, but take this into account whenever you start formulating your problem. So let's see if I wanted to say something else here. Oh yeah. So this is just inviting you to think beyond these fairness-aware machine learning approaches. And then a final thing that's especially important in this scenario is that these pretrial risk assessment tools, like right now we have optimized for equalized odds because we assume that, you know, if it's a positive prediction that something will happen or will not happen. But in the United States, these tools are not used for automated decision making, but they are used as decision support for the judges. So this could also influence the way in which you evaluate the fairness of a model, because even if you create the most fair model according to whatever metric you're interested in, if the judge just uses it in a different way, then this could still affect the fairness outcome of the system as a whole. So for example, if the judge maybe unconsciously uses a different decision threshold, so to speak, for African Americans compared to Caucasians due to their own unconscious biases, then even if you have created the most fair risk score model of the world, it will still not solve the actual problem because the judges are interpreting things in a different way. So this is just also important to keep in mind in all cases. What are we coming from? What are the possible consequences of doing things? For example, if we know that this model is used as decision support, maybe it's more important to have it interpretable compared to some other scenario. So these are just some things that I would like to, I would like you to keep in mind. I see I finished a bit earlier, but I think that's fine. So maybe if people still want to hang out and ask questions or just discuss other fun things, that's also fine. And otherwise, I would like to thank you a lot for your attention. And I hope you keep coming to these awesome PyLadies events, because I think it's really cool the way in which these are organized. It's really a lovely community. So highly recommend. So that's it for me for now.
Thanks. I have a question though. So actually you're speaking lots of this Fairlearn library, and you're one of the maintainer. What kind of help is needed right now for this library? How we can help you as a community?
Ooh, that's a really good question. I'm just going to stop sharing my screen so
Sure.
I can also easily see you all again. All right. Now you don't see my screen anymore, right?
Yeah, we don't see it anymore.
Yes, all right. So in Fairlearn, we actually we have a lot of things that still need to be done. So first of all, we have on the more technical side, we have a bunch of algorithms from papers that we still want to implement, and also on the measurements side, so how we actually can measure fairness, there's also some things that we are working on. But we are also quite actively thinking about developing better learning resources for people to learn about these issues. And it's quite, I have to say, it's a lot of fun because it's such an, first of all, it's a really great community. I mean, you can imagine that the subset of people who are interested in fairness is generally quite a nice set of people, at least in my view, because they care about things. But we are developing also these learning resources, and it's quite interesting because it's generally in open source projects, it's usually a lot about technical details about things, but fairness is of course also very much a socio-technical issue, right? So that makes it a lot more tricky, and it requires a lot of different types of expertise to actually create good learning resources to help people put this into practice. So that's something that we're working on as well. And we definitely also have a lot of people in the community who are not maintainers. Actually, many people who are maybe not immediately don't feel comfortable to write a bunch of code for a library, who help us with the documentation and then also with the learning resources. It's actually also a lot of fun and really cool to see what people come up with. So yeah, actually we require help in all states.
Awesome. Yeah, and for beginners, is there something you would recommend?
Yeah, so we have actually we use the same tagging as for example Scikit-learn has. So we have like on
Good first issue or
yeah,
something?
exactly. So we have easy, good first issue, help wanted, all the typical
Okay.
tags, which you can just find on our GitHub issues list. Yeah.
Okay, perfect. And there's also a question in the YouTube chat. Would you automatically get more false positive rates if the first arrest frequency is higher in the non-Caucasian groups?
Wait, I need to. It's always difficult if I don't read it myself.
I can maybe put it in the chat.
Yeah, that would be great. Wow, now I realize how much I rely on reading things instead of hearing them.
Yeah.
That's
And
funny.
sometimes for longer questions, you need to read. So
Let's see. Okay, so would you automatically get more false positive rates if the first arrest frequency is higher in the non-Caucasian group? So I'm not exactly sure what this question asks, but there is this relationship between the base rate in the data set. So basically the proportion of positives that's already in the data set itself. And if that is different, which is the case in this scenario, between one group versus the other group, then if you use the same decision threshold, it will actually always result in not equalized odds. That's like, you can prove that mathematically. I think I also discussed it in the previous workshop, but I'm not really sure. So if you want
I
to, you
think you
can
did.
check
I
out
think you did.
the beginners workshop of PyLadies. It's somewhere in the last part of the notebook. I explain that part. So that might be a useful resource to learn more about that.
There is a clarification in the chat. He says that black people get arrested more frequently. So, will that lead to more false positives in the non-Caucasian?
Yeah. So that's, yes, exactly. Yes. So because there is this difference in the base rates, so in the proportion of people that get arrested, that will, if you use the same decision threshold, that will automatically work like that. I mean, it's quite, I always like to visualize that, but you can imagine that if the distribution is skewed to this side for one group, if you have to pick one decision threshold, then automatically the group that's more skewed to the right will get more positives even if they weren't positive. So that's but it's difficult to explain without the visualization itself. But I hope that's clear. But that's a very good observation, yes. And I see there's another question. Have there been any fairness algorithms put into practice? So I do know there are people who are using the Fairlearn library in at least developing their models. I'm not really sure if they're actually being deployed or not. I know that this Fairlearn library started out as a Microsoft research project, but it's now fully open source, also without Microsoft governance, like open governance, yada yada. But I know that within Microsoft there have also been some case studies where at least they have worked on solving fairness related issues. But I'm not 100% sure which algorithm would be using these fairness aware mitigation approaches.
Okay. I have a question of my own also.
Yeah.
I think in the exponential gradient, you were talking about interpretability, and I think one of the whole reason that ProPublica did this research was because they couldn't get access to the actual algorithm. So I think it's always a bit, sometimes the algorithms are not interpretable at all. And sometimes under the hood of corporate security and
for sure. Yeah, so that's
algorithmic.
also that's a very, very interesting point that you mentioned. So that's there's this very interesting paper by Cynthia Rudin, and what she does there is she actually tries to, because indeed Compass is proprietary, so you cannot actually understand what's going on in there. It's supposed to be based on hundreds of variables, based on like surveys that people fill out or whatever, something like that. And then it turns out that you can easily reproduce COMPAS scores using a logistic regression model with two features, namely age and the number of prior arrests. Those two features. So, and the point that Cynthia Rudin makes in that paper is if we know that it only depends on two features, we can have a conversation about whether we think that's okay or not. Because basing something on age plus prior arrests, like if again the arrest rates are can be conflated for some groups, inflated for some groups compared to others. So we can wonder if that's the best thing to do. But we can at least have a conversation about it if we know exactly what's going on. By using some sort of a proprietary algorithm, it's much harder to have that conversation, and we can only focus on these outputs. You see the same thing with the child care benefit scandal in the Netherlands, right? It was super simple algorithm. I don't think I would even call it an algorithm. It was a rule. And then still, how much harm was there? Like it's I can use this example. So I teach a course called Responsible Data Science on a bachelor's course. I can use this example in each and every one of my lectures because it fails on accountability, it fails on interpretability, it fails on fairness, probably also privacy. I'm assuming that probably they also screwed it up with the privacy because I mean, the amount of people that had access to this data and this blacklist and everything was probably too high. I don't know that for sure, but I mean, with everything else that went wrong, I'm assuming that would also go wrong. So it's quite, yeah, it's that's like beyond just fairness. This problem of accountability, of being able to have some meaningful recourse, so be able to actually, say, why was this decision made? I don't agree, and do not just get the answer because the algorithm said so. That's also a very important part of responsible machine learning. So fairness is only one thing that we can focus on. So that's a very long.
I think we need a whole session about it.
I think for those who wants to ask questions, you have the last shot to do it.
Yes.
So feel free. By the way, you can not only type, you can also unmute yourself, show yourself if you want, and ask it. You have still this awesome chance to talk to Hilde right now, right here, right now.
Well, in Fairlearn, I'm just going to do some more more advertisement. We actually have a weekly community call on Thursdays at 5 p.m. Amsterdam time. And that's actually quite a lot of fun, and it's also open to everyone. We have a Discord channel that you can join. And so if you want to learn more about fairness, then I would definitely recommend to maybe hop on a call, or if you are interested in contributing to Fairlearn, that's also everybody's welcome. In absence of questions, just going to do advertisements.
I think it's pretty great idea. I just want to say like one thing. I do a lot of, let's say, so-called industrialization of MLOps, and frankly speaking, the point. So a lot of companies still struggling even with the basic monitoring for machine learning. Yeah. Not speaking about fairness, interpretability. Yeah. So they only start, let's say, making their first steps in the direction. Let's start monitoring because we get complaints from the end user that something going wrong with predictions. So instead of doing it, let's say, reactively, let's start doing more proactively. So probably we could start monitoring like feature drift, like are there any skew in distribution. That just some basic first steps for it. And then the companies realize they don't have infra to do it at all, because it's usually also like a really, really huge thing. But yeah, I think what really, really important to add here, that I think like the whole process of responsibility, interpretability, it should be incorporated. It should be must-have in case if the predictions can in any, let's say, way harm an end users. Yeah. Because if it's something like, I don't know, like basic calculations of something rule-based for internal things that doesn't gonna make a lot of harm. Probably you can skip it if you need, something fast. But I would say if the end user is there and if there is a like potential harm, I think it should be must have. But it also must have should be not in the sense there is like a checkbox. You said,
Yeah.
oh, it's fair. Like
Yeah. It's a good point also about this. It's something I notice a lot in my class, for example. In order to really understand and do responsible data science, you first need to be able to actually do proper regular data science. Like sometimes you see students who, for some reason, I don't really know what goes wrong, but who do not understand even train test splits, like so basic things like that. Like if you do not, like the first step is doing data science properly, and actually if you would do things properly, a lot of these harms would not exist, because you would be thinking carefully, should I use machine learning? How should I phrase my problem? What are potential consequences of phrasing my problem like this, right? These are all the things that if you would be doing data science and machine learning in a very conscious way, you could already avoid so many harms by just listing them before you even start. Like, what are the consequences that can happen if you do this? Which is, of course, much easier in hindsight when we have all these examples of how things might go wrong, right? So it's always very easy for me as a researcher to say, you should do this, when you have the reality of working in a company with deadlines and blah, blah, blah. But yeah, I like to be the nagging voice in somebody's head.
I think it's a really nice phrase actually to put a huge dot on this evening. So first of all, thank you so much, Hilde, for being with us twice. I do hope that you get much more people who can help support Fairlearn further. And once again, like at time, you can support it or pure technically by coding, or even you can support it with writing documentation, adding nice learning cases. So it's up to you if you're afraid to do first commitments. If it's too much for you in case of coding, you can always start going from the soft parts, and then you can always switch to the more when you get more confidence. And I'm pretty sure that the Fairlearn team will be really happy to have you on board.
And very helpful people, I would say. So like if at any case you're stuck, always happy to help.
Okay, thanks. I think we can right now shut down the stream, right?